Welcome to Lasea class. I am your teacher, Jan Lasea. Today, we study key means clustering in machine learning. Clustering or cluster analysis is the task of grouping observations such that members of the same group or cluster are more similar to each other by a given metric than they are to the members of the other clusters. Some applications of clustering. Clustering is commonly used to explore a data set. Social networks can be clustered to identify communities and to suggest missing connections between people. In biology, clustering is used to find groups of genes with similar expression patterns. Recommendation systems sometimes employ clustering to identify products or media that might appeal to a user. In marketing, clustering is used to find segments of similar consumers. There are plenty of algorithms to learn in machine learning. Under clustering, let us understand the k-means clustering. Types of systems of machine learning. The supervised learning means it learns from previous examples. For example, a car has 4 wheels. Therefore, if a new object has 4 wheels, it could be a car. The data that you fed into the algorithm with the desired solution are referred to as labels. Some examples of supervised learning are k-nearest neighbors, linear regression, logistic regression, neural networks, support vector machines or SVM, decision trees, and random forests, to name but a few. On the other hand, unsupervised learning means inferring a grouping without any label to learn from. For example, a list of items all have roots and are made of wood, so they should go into the same group even though they lack a name. The data is unlabeled. It means it finds patterns, solutions, and clustering. Some examples of unsupervised learning under the clustering, such as k-means hierarchical cluster analysis. Under the association rule learning, we have ECLAT, a priori. Under the visualization and dimensionality reduction, we have kernel, PCA, T-distributed, and principal component analysis, to name but a few. The k-means algorithm is an iterative process of moving the centers of the clusters, or the centroids, to the mean position of their constituent points and reassigning instances to their closest clusters. The variable k is a hyperparameter that specifies the number of clusters that should be created. K-means automatically assigns observations to clusters, but it cannot determine the appropriate number of clusters. Therefore, the data scientist, the programmer, should be the one to choose the value for the hyperparameter k. Computing distances for learning. An algorithm can learn by using vectors of numbers that use distance measurements. Open the space implied by your vectors is a metric 1. That is, a space whose distances respect certain specific conditions. Number 1. No negative distances exist, and your distance is 0 only when the starting point and ending point coincide. It is called the non-negativity. Condition number 2, the distance is the same going from a point to another and vice versa. It is called symmetry. Lastly, the distance between an initial point and a final one is always greater than, or at worst the same as, the distance going from the initial to a third point and from there to the final one. It is called the triangle inequality, which means that there are no shortcuts. Distances that measure a metric space are the Euclidean distance, the Manhattan distance, and the Chebyshev distance. These are all distances that can apply to numeric vectors. In geometry and pre-calculus, we learned the distance formula between 2 points on a Cartesian plane. This is the Euclidean distance, named from Euclid, a Greek mathematician. The formula of Euclidean distance is the square root of the sum of the square difference between the 2 points. For example, the Euclidean distance between the point 1, 2 and 3, 3 is 2.236. Number 2, the Manhattan distance. The formula of the Manhattan distance is the sum of the absolute difference between the 2 points. For example, the Manhattan distance between the points 1, 2 and 3, 3 is 3. If the Euclidean distance marks the shortest route or route, the Manhattan distance marks the longest route, resembling the direction of a taxi moving in a city. The distance is also known as taxi cab or city block distance. Number 3, the Chebyshev distance. The formula of Chebyshev distance is the maximum between the two absolute difference between the 2 points. For example, the Chebyshev distance between the points 1, 2 and 3, 3 is 2. The maximum between 2 and 1 is 2. The key-means algorithm is summarized into 5 steps. Step number 1. Input the value of k, which is the number of clusters. Step number 2. Choose the location of the initial k centroids or the centers of the clusters. Step number 3. For each data point, find the distance by applying the Euclidean or Manhattan or Chebyshev distance to each of the k centroids and assign the point which is nearest to that one. Step number 4. Once all the data points had been assigned to a cluster, recalculate the centroid or the center positions. And finally, step number 5, repeat step number 3 and 4 until convergence is met, when it has lower sum of squared errors. This is an indication that the centroids have converged to better locations and therefore to a better local optimum. Determine the value of k using the elbow method. If k is not specified by the problem's context, the optimal number of clusters can be estimated using a technique called the elbow method. The elbow method plots the value of the cost function produced by different values of k. As k increases, the average distortion will decrease. Each cluster will have fewer constituent instances, and the instances will be closer to their respective centroids. However, the improvements to the average distortion will decline as k increases. The value of k at which the improvement to the distortion declines the most is called the elbow. Take a look at this elbow graph. The average distortion decreases as k increases from 1 to 5. There is a little improvement for values of k greater than 5. Therefore, we can select k value of 5 as input to the k-means algorithm. The k value of 5 is the elbow. Silhouette coefficient. Sometimes the elbow graphical method is not certain in determining the value of k just by looking at it. To evaluate the performance measure for clustering, we use the silhouette coefficient. Silhouette coefficient or average silhouette coefficient is a measure of the compactness and separation of the clusters. It increases as the quality of the clusters increase. It is large for compact clusters that are far from each other and small for large overlapping clusters. The silhouette coefficient is calculated per instance. For a set of instances, it is calculated as the mean or average of the individual samples scores. The formula of the silhouette coefficient or the average silhouette coefficient is equal to the product of A and B divided by the maximum of A and B, where A is the mean distance between the instances in the cluster, while B is the mean distance between the instance and the instances in the next closest cluster. The silhouette coefficient or average silhouette coefficient value has a range from -1 to +1. To interpret the meaning of the silhouette coefficient value, we refer to this table. The silhouette coefficient value near to +1 means that the sample is far away from the neighboring clusters. Therefore, the sample is well clustered and already assigned to a very appropriate cluster. If the silhouette coefficient value is near to 0, it means that the sample is on or very close to the decision boundary between two neighboring clusters. Therefore, the sample could be assigned to another cluster closest to it, and the sample lies equally far away from both the clusters. That means it indicates overlapping clusters. If the silhouette coefficient value is near to -1, it means that the samples might have been assigned to the wrong cluster. Therefore, the sample is misclassified and is merely placed somewhere in between the clusters. Therefore, the silhouette coefficient value near to +1 is the best performance measurement for clustering. Clustering analysis Python libraries. The scikit-learn or sklearn, this library implements the Euclidean distance. On the other hand, the PyClustering library implements the Euclidean, Manhattan, and Chebyshev, Canberra, and chi-square computing distances for learning. The k-means clustering example code that I will provide uses the scikit-learn library. The example dataset to identify the clusters or groups using k-means clustering is the mall customers data set. The mall customers data set consists of fields, namely customer ID, genre or gender, the age, the annual income in thousands of dollars, and the spending score rate from 1 to 100. The mall customers dataset has 200 records. The independent variable y, or the target variable, is the spending score, while the dependent variables x are customer ID, genre, age, and annual income. Select the features. And in key means clustering, we need to select or specify the features to be clustered or grouped. There are many combinations of selection, and I listed only 6. Selection number 1 has 2 features, namely annual income and spending score. Therefore, it is 2 dimensions. Selection number 2 has 2 features, namely age and spending score. And also, it has 2 dimensions. Selection number 3 has 3 features, namely age, annual income, and spending score. Therefore, it is 3 dimensions. Selection number 4 has 2 features, namely genre and spending score. Therefore, it is 2 dimensions. Selection number 5 has 3 features, namely genre, age, spending score. And it is a 3 dimensions. Finally, selection number 6 has 4 features, namely genre, age, annual income, and spending score. And it has 4 dimensions. Beware the curse of dimensionality. The curse of dimensionality is the realization that the number of data points required to sample a space grows exponentially with the dimensionality of the space. The curse of dimensionality was termed by Richard Bellman in the context of dynamic programming. If we keep adding features or dimensions, our space becomes sparser or thinly spread with many spaces in between. It is due to this sparsity that we require a larger and larger number of data instances when dealing with higher dimensions. 1, 2, and 3 dimensions are fine, but higher than 3 dimensions is difficult to see the visual graph. It is natural for us that we live and see things around in 3 dimensions. If we select the 2 features, namely annual income and spending score, and compute the average silhouette score of k values from 2 to 6, then the highest and near to positive 1 average silhouette score is 0.554 with k equals 5. The average silhouette score declines when k is greater than 5. This is the graph result of k-means clustering of the 2 features, annual income and spending score, with 5 clusters. The red dots are cluster number 1. The blue dots are cluster number 2. The green dots are cluster number 3. The cyan dots are cluster number 4. The magenta dots are cluster number 5. The stars represent the centroids or centers of every cluster. If we select the 2 features, namely age and spending score, and compute the average silhouette score of k values from 2 to 6, then the highest and near to the positive 1 average silhouette score is 0.5 with k equals to 4. The average silhouette score declines when k is greater than 4. As we can see, the average silhouette score declines when k is 5 and K is 6. K is greater than 4. This is the graph result of K-means clustering of the two features age and spending score with 4 clusters. The red dots are cluster number 1. The blue dots are cluster number 2. The green dots are cluster number 3. And the cyan dots are cluster number 4. The stars represent the centroids or centers of every cluster. If we select the three features, age, annual income, and spending score, and compute the average silhouette score of K values from 2 to 6, then the highest and near to positive 1 average silhouette score is 0.52 with K equals to 6. The average silhouette score declines when K is greater than 6. This is the graph result of K-means clustering of the three features, age, annual income, and spending score, with 6 clusters. The graph is plotted in 3 dimensions. The red dots are cluster number 1. The blue dots are cluster number 2. The green dots underneath are cluster number 3. The cyan dots are cluster number 4. The magenta dots are cluster number 5. And the orange dots are cluster number 6. The stars represent the centroids or centers of every cluster. This is the summary of the 3 sample selected features. The highest average silhouette score has 2 features, annual income and spending score. Therefore, we can select these features for clustering the mall customers. However, we can also select the second place that has 2 features, age and spending score, when age has high correlation towards the spending score. These are the codes for K-means clustering written in the Python programming language. At line number 31, it loads the mall customers data set. At line number 34, we select the 2 features, namely annual income and spending score. At lines number 39 to 50, it uses the elbow graphical method to find the optimal number of clusters. At lines number 53 to 75, it chooses the value of K from the max average silhouette score. At line number 80 to 81, it builds and evaluates the model, the K-means model. At line number 86, it trains the K-means model. At line number 94, it predicts the cluster labels. At lines number 102 to 104, it plots the 2-dimension clusters. At line number 107, it plots the two-dimension centroids or the centers of the clusters. Finally, at lines number 116 to 137, it is an input test for prediction. By inputting the annual income and the spending score, it will predict what cluster those samples belong to. Let us compile, run, and test. It displays the elbow graphical method that shows the number of K from 1 to 9 and then the average dispersion. And we can see that the elbow is around K equal to 5. Next is it displays A graphs of the different values of K from 2 to 6 with their computed average silhouette score. The highest average silhouette score is 0.554 with K equals to 5. Next, it shows the graph of the 5 clusters of the 2 features, namely the annual income, which is the independent variable X, and then the dependent variable Y, which is the spending score. We can also read some messages that the total records is 200, the chosen K clusters is 5, and the identified cluster labels are from 0, 1, 2, 3, and 4, and the coordinates of the cluster centers or centroids are the following, and then the average silhouette score is 0.55393 or 0.554. Let us have a input test for prediction. Please enter the annual income in thousands of dollars. I input the value of 15K. Please enter the spending score. I input the value 39, and it predicts that the annual income of 15 and the spending score of 39 belongs to cluster number 5. Do you want to input another sample? Yes. Enter the annual income. I type 23. The spending score, I type 98. The predicted cluster is 4. Do you want to input another sample? Yes. I input the annual income 50. I input the spending score 49, and it predicts that the annual income of 50 and spending score of 49 belongs to cluster number 2. Do you want to input another sample? No. That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.